GEMA webinar. We are privileged to have among us Mr. Ratnadeep Sinha as the speaker from the industry. Mr. Ratnadeep Sinha is Proportional Engineering Head from Thermax PES, EPC Wings of Thermax Limited. Earlier, he was Head of Detailed Engineering of Thermax PES Division. He has 30 years of experience in design and engineering of EPC projects in India and abroad, from concept to commissioning, which includes project in field of petrochemicals and power plants. He brings the perspective of value engineering in project business. I invite our knowledge partner to start knowledge share. Over to you, Mr. Sinha.
Thank you very much. I'll just share my screen. Give me 2 minutes.
Yes.
So my screen is visible to everybody,
Yes, sir, your screen is visible.
and my voice is okay.
Yes, sir, your voice is also okay.
Yeah. Thank you everybody for joining this webinar. And I've made a small presentation of around a few slides. Basically, I would like to discuss the steam and power requirement, the utility part of it for a 1G ethanol, and how to select, and also try to understand and also discuss about what are the pain areas during the selection and how it will be helping the industry. So that is the basic theme of this particular presentation. So basically, we are going to discuss about what is combined heat and power system, and evaluation of power demand, how to evaluate the steam demand, and how to configure a cogeneration plant. Then we'll touch upon the selection of boiler, turbine, and some important considerations which I think it is important to discuss. See, this discussion, though it is specifically for the ethanol plant, but just a minute. Hello? Sorry. Though it is specifically for an ethanol plant, this perspective I am bringing from the overall cogeneration system in the market, which today there are a lot of ethanol plants of different capacity, from a smaller capacity to larger capacity. And I believe that the capacity, as the government is going for higher amount of petrol, mix of ethanol into the petrol, though, so the capacity will be more further larger. So in that perspective also, we need to think how we can shift from the present cogeneration system to a future higher megawatt and higher steam consumption for the ethanol plant, and how to select that. So basically, I am Ratnadeep Sinha. I'm working in Thermax Limited in PNDS. PNDS, as you know, is a EPC wing of Thermax. So I have experience of last around 30 years working basically in the power field, also in the process, as well as in the petrochemical field. So we'll start the discussion that in a conventional system, if you see the conventional system where we can have a boiler, we can have a steam turbine, and getting the steam turbine run for the power, and we can just take steam from the boiler. In that, you will find that overall efficiency of the system is around 35% of the electrical output you get, and there is a huge loss which is coming out of, say, cooling tower. Basically, it is going to the environment. But however, when you are talking about CHP, basically cogeneration plant, you will find that around 50 to 60% useful heat, or in sometime if the cogeneration is more, you can go for 70-75% useful heat we can use. And obviously there will be certain losses, and then which will be around 15% to 20%, and electrical power output will be 35%. So your steam generation and the power generation will happen simultaneously, which is enhance the overall capacity and overall efficiency of the power generation and cogeneration system basically. So you will have basically a fuel efficiency, whatever fuel you are going to select, coal or biomass or whatsoever. So you will find that there is a energy efficiency enhancement in the CHP, and there is a biomass system based CHP. So there you have an advantage about the green energy in that sense, and there is a operation reliability because these cogeneration plants are in existence for long years. So it is a established technology in the market. So if we select the system properly and if we select the boiler technology and the turbine technology properly, it is going to be a reliable source of your utility, the basic utility, steam and power. And obviously, based on the selection, we can see how it will be environmental friendly, and finally, whatever economic benefit it is going to yield for the yield for the business. So first, just for a starting point, you will find that this is the starting point for any cogeneration plant selection. So there is a steam turbine, there is a boiler, everybody of us knows. And so it starts with a preparation of somebody has to put a heat and mass balance into place. So we should know, so there is a steam turbine, and in that we should know what is the steam you require. Just a minute. So what is the steam you require? So this is the cogeneration portion of it, and then there is a boiler obviously, and then selection of the feed water heaters. So this is also very important, which I'll cover it in the subsequent slides. The how feed water systems is important. This system can be condensing also, can be back pressure also. So that selection criteria also we are going to discuss. See, this I have taken a sample from a cogeneration plant where they are using a broken rice. Is one of their feed for the ethanol. So, and the megawatt can vary based on your power demand. So that portion also is going to be covered in particular webinar. And there will be a deaerator, which is basically contact type feed water heater, and also it is required to scavenge oxygen from the system so that your boiler corrosion comes down. So basically, if you see the CHP plant, after you somebody develops a CHP plant, I'm just going to discuss this point how someone is going to evaluate the efficiency of the feed of a plant. So there is a fuel which is coming as as a input input to the plant, and then obviously the power is the output, and I'm considering the entire power system as a black box and the boiler as a black. Sorry.
आगे ट्राई करके देखो आगे का सपोर्ट आगे तो आगे भी ऐसी रखी हुई है
I think if somebody can mute it, it will be helpful for us. So there is a power cycle, and then there is a boiler, and the heat is getting input basically in the boiler, as you all know, and the heat is coming out of the boiler as a high pressure steam, which is entered into the turbine in the power cycle, and we are getting power as the output and process steam as the output. And also, when you are giving a process steam from ethanol plant, some of the, I think 70 to 75% condensate also is coming back to the system, and there is then and balance 25-30% is going to be a water makeup in form of a DM water. Basically it will be coming to the deaerator. That's why I have shown it here. Finally it is going to come to the boiler. So if you see the plant heat rate calculation, then you will find the plant heat rate is a function of all these output and input. So if you see the input and output formula, you will get that the output is the power. So this is the power, and then in the top portion it will be the input, that is your HP steam energy, and the output is going to be a feed water which is going to the boiler. And again the condensate return, there will be small heat which is coming to the system, and the makeup water, some small heat coming to the system. So if you do the arithmetic out of it, you will get the plant heat rate. Basically, plant heat rate is the indicator of the efficiency of the plant. So if you inverse plant heat rate, that means 860 by the plant heat rate, you will find the efficiency of the plant. And why plant heat rate is there? Because you will find this kilocalorie per kilowatt hour. That means to generate 1 kilowatt of power, you require so much of heat. And if you divide this plant heat rate kilocalorie per kilowatt hour with the GCV of the coal, you will find coal or the fuel, you will find what is the fuel consumption. So that is how one should start evaluating the plant efficiency, which is very important for the capex calculation and the creating the capex model for your cogeneration plant and the overall ethanol plant as well. Here, the point is to be noted that in many of the plant, what we are seeing that they are using only boiler, say low pressure boiler of around 22 or 10 bar pressure and around 22 25 for a typical 150 kLPD or 200 kLPD plant or maybe 300 TPH boiler. So in that case, you have to have a clear understanding that your power is reliable, which is coming from the grid, and the cost of power also has to be compared with respect to a combined heat and power plant versus standalone boiler of a low pressure process boiler, and the power is purely coming from the grid. So you need to have a calculation and the comparative out of it. So if you see the first part, what we have to calculate is the evaluation of the power demand. So if you see, obviously you all know you are all coming from this industry. So grain handling, liquefaction, fermentation, distillation, dehydration, evaporation, and drying. So and utilities, of course. Utility includes power plant. So here you have to calculate the power demand. I'll come just now in the next slide how to calculate this power demand. So all this power will constitute of a power demand, and also you need to see that whether you are connected to the grid. Why it is important when you are connected to the grid? So you will have a facility to extract power from the grid as well as supply power from the grid. So accordingly, you will have an agreement. See what is the minimum power demand of the grid, whether you will be allowed to put some power back to the grid, because in some time if you put the power back to the grid, they can put a charge out of it. So all this thing has to be taken into account while sizing the plant, and also the Opex estimate for that. Obviously based on the configuration, you will finally come to the capex estimation, but first we have to find out what is your Opex estimation. So also you have to understand that with all these systems, the grain handling, liquefaction, fermentation, and basically in India, as we all understand, it is a batch process. So all the drives are not running simultaneously. So some drives we can define as a continuous drive. Some drives we can define as an intermittent drive. And I don't think I think we are again clarifying that intermittent drive and the standby is different. Standby, even if it is a hot standby, it is not going to operate though it is connected to the system. Intermittent drives are those which is connected to the system and it is running. However, it is not running 24 by 7. It is running say 8 hours a day, 16 hours a day. So for example, if you see, so you have to make a chart like this. So there is a rated power. So first of all, you have to divide the entire system in the systematic manner, like this: grain handling system, liquefaction, fermentation, distillation, evaporation, and drying. And then you have to uh, write down all the drives. Maybe in the preliminary stage, some small drives can be missed out, which we can consider as a contingent power, because there will be some small drive which we may not be able to envisage during the preliminary stage of of our design. So in that case, so this chart has to be made, which we call as the load list. So in that we decide what is the total number of drive, what is the estimated power of the drive, and that can be taken from your past project or some of reference project, and that can also be prorated based on the capacity. So if somebody have a 200 kLPD backup and he wants to enhance to a say 250 kLPD or 300 kLPD, in that range, it has to be in vicinity. So this can be prorated accordingly, because initial period you will not get all the exact values, and that is fine. So but we know the system, so we know what are the total number of drives which is coming, and out of that how many is running and how many are standby. So for example, in this particular case, so grain chain conveyor is around 3.75 4 kilowatt rating, and this will be one operating and one is running. There is no standby in this case. And Second, then the grain bucket elevator, there is no standby. But then motorized gate, chain conveyor, you have one working and one standby. So this is one consideration. So first part of the chart you have to make like that. So rated power, then the quantity. And the third part is coming, what is the running load? So while calculating the running load, you have to find out, see, these are all motor capacity. These are the motor rating. And when you are talking about, and right now I am not considering any VFDs here. So though it is, so whenever I am selecting a motor of 3.75 or 5 kilowatt or 7.5 kilowatt, obviously the power consumption is not going to be 7.5. So there has to be a factor which we call as a diversity factor. Generally in industry we take around 0.85 to zero point 0.8 based on the so if you have a conservative estimate, so you have to take around 0.85 as a diversity factor. So if the motor kilowatt is 75.75 kilowatt or 10 say 10 kilowatt, so 10 kilowatt we should take a, for the power calculation we should take a 8.5 kilowatt as a power consumption. And if there is a VFD, this factor can be further reduced to zero point 0.7 to 0.75 because that amount of power saving you will have. Now, then we have to calculate what is the hour of operation. For example, this is a grain handling system. In this case, this is operating for 8 hours, say. So if it is 8 hours, so our power consumption for a day, average for a day. So power consumption, we are talking about average for a day. So power consumption, we are talking about 8 hours a day for this particular grain handling system in this case. So in that case, I have to multiply the factor as, after multiplying with 0.85, I have to multiply it for this case, say 16 hours a day I have taken 5.67. If it is 3 hours, 8 hours a day, so this will be multiplied by 8 by 24. So that is how we should calculate the intermittent power. Fine. Now, after that, there is an Opex estimate and the Capex estimate. Now, what is Opex estimate? Opex estimate is the power which you are going to consume, predicted power which you are going to consume. So in that case, we are going to sum up all the running loads which are continuous and all the load which is intermittent, where I am putting this kind of factor of 0.67 based on the running hours of the particular drive. In some cases it is 8 hours, so it is 8 by 24. If it is 16 hours, so 16 by 24, something like that. So that much of diversity I have to add, and obviously some utility power we have to add. That is, this utility power basically whatever we are going to consume for the power plant itself. So with all these things we can calculate how much power you are going to consume for that particular ethanol plant, and that is going to be an operation expense. Because in a part, for suppose you are having a 200 KLPD plant, so that much of power you are going to consume. So whether you are taking from grid or you are taking from a cogeneration power plant, so that much of cost you are going to bear, whether it is a grid power or whether it is a power plant power. However, for the capex estimation, now if I have to contract with the grid, that how much power maximum I am going to consume, or you have to size a steam turbine generator where you have to find out what is the maximum power you are going to consume. There, you cannot put that factor. You cannot put the factor because in some point of the time when the say for one drive is running for 8 hours, but the continuous drives are also running, so that time I cannot put that factor in place. So that time I have to take the all the continuous or intermediate load, all the sum, and try to find, and all obviously utility power, and try to find out what is the total megawatt for which I have to design the power plant, or I have to contract with the grid for the maximum power. Then obviously after finalizing the power generation portion, we have to go to what is the steam generation portion. And as you guys all know that for the mash cooking, it is a very high demand. Liquefaction, fermentation, it is a moderate demand of steam. For distillation and the evaporation and is the high demand, and drying system is a very high demand. If I divide the entire steam generation portion of it. Now then you have to, then obviously I am not going to touch upon the portion. This is a separate subject altogether. How to optimize the steam demand by evaporation, heat recovery in distillation, wet cake utilization, or maybe MVR portion. So this portion I am not discussing. So with all this optimization, as a assumingly is in place, you have to find out what is the final steam demand continuous and what is the steam demand maximum. So normal and maximum steam demand you have to calculate, because finally this steam demand you are demanding from a steam turbine when you are going for a cogeneration plant. If you are taking from a boiler, if you are taking from a boiler, only a process boiler, it is very easy. You steam demand, you can take a 10-15% margin or 20% margin, and and size the boiler. But it is not so easy when you are going to size the cogeneration plant where you are taking extraction or you are making a back pressure turbine for the plant. So here you have to be very careful, while, because you cannot over specify, you cannot under specify, you have to be in optimum level while specifying the steam demand. So what are the factors while you are configuring a cogeneration plant is, first of all, the selection of steam turbine, then whether you have a grid connection or not, whether you are going for a totally islanding mode of operation and you are cut off from the grid, and what is the plant PLF, means you are sizing a 300 KLPD plant. What is your expectation that it is in the next 5 years after commissioning or 7 years after commissioning, it is going to run for 100% load or 80% load on average or 75% of the load? That obviously that portion you guys are much better judgment, but that also is to be taken into consideration. And obviously based on your feed available and the amount of offtake you can deliver to the buyer, you also need to understand what is the fluctuation which is going to happen in your ethanol plant, because all these are going to affect the cogeneration plant sizing. So first of all, when we are talking about the steam turbine, we have to find out that why I'm talking about turbine, the boiler selection criteria are different. So I have taken into a separate discussion in this particular webinar. So on a steam turbine, we have to find out what is whether you are going to use a back pressure turbine. These days, obviously, almost everybody of you are using or going to use back pressure turbine. But what I find that when the plant capacity will be go higher and higher, say 600 KLPD, tomorrow it may be 800 KLPD. In that case, your power demand and steam demand also is going to be increased proportionately. Then we need to also think whether we are going to use a extraction condensing turbine or not, because very high capacity or the moderate capacity of back pressure turbine will be a challenge tomorrow, considering the fluctuation, whether the grid demand is there, whether how much accurate we are in the steam calculation. So all this, considering that, sometime end of the day when we are going for a higher capacity, we may look into a extraction condensing turbine. Secondly, whether you are going to sync with the grid or we are going to operating in the islanding mode. This also affects the design, because when you are going to sync with the grid, your power demand, or whether you are creating excess power or you have some shortage of power, finally it will be balancing of the with the grid. But when you are in the islanding mode, then you cannot depend on the grid, so you are on your own. So accordingly, the margins and the selection of the turbine should be done. And obviously the load fluctuation, how much you are expecting, that you have to decide. So with all these things, you will come to know, as I discussed, there will be a heat and mass balance diagram, and after that we will select the boiler. We'll come to the portion how we are going to select the boiler. Then whether we are going to put the feed water heaters, because whether it is going to advantage for you or whether it is not going to advantage for you, and whether you are going to use a drum condenser. So all these things has to be taken into consideration. I'm coming to that portion in the subsequent slides. And also, just one check you have to carry out, and you all know that when you are going to sign a contract with the grid, the power distribution boards, you have to sign for a minimum demand. And how much minimum demand you are going to put is very important, because end of the day, if you do not take minimum demand, you will get penalized. So one hand you are generating power by consuming fuel, coal or biomass. Other hand, you will have a minimum demand charge. So that also has to be taken into consideration when you are going to select a cogeneration plant. And finally, obviously, the final model will be coming based on the what is your operation cost and the capital cost, of course. So coming to steam turbine, for this process industry, basically two types of. I'm not going to the intricacy of the steam turbine types. I'm just going to the overall type of turbine. What is the so there is a back pressure turbine, as we all know. So in the back pressure turbine, steam is given to the turbine, and it is extra. So steam is given to the main steam is coming to the turbine, and the process steam is taken and is going to the process. And if the temperature control, you may put a desuperator here. So this is a simple back pressure turbine. In a back pressure turbine, obviously the exhaust steam is in high pressure, which is ideal for your process. But here the challenge is like this: the control is a challenge. The balance between the power and the steam is a challenge, because uh, it is possible during the we may do a calculation in our in our Excel sheet, in our model, in our HMBD, but end of the day, if the power demands goes high and your steam demands is fixed, so I cannot increase the power because my steam demand is fixed. I cannot put the steam anywhere else. So how much the amount of steam I give, the power will increase in that proportion. Or if I demand more steam and my power is fixed, I also cannot extract more steam, simply because I cannot give the power anybody else other than so it is important to understand, understand that how the grid is connected with this system. So generally what happens, if your steam demands increases, power generation increases, so the balance off taker of the power will be the grid, or vice versa. So if your power demand increases and steam demands remains constant, so your additional power has to come from the grid. It is like that. So that is why the fluctuation is very important. Fluctuation and the accuracy, how much accurate we are, near about accurate in our estimation of power and the steam, is very important. So if we start over designing the thing, suppose I decided my power demand is say 14 megawatt and I purchase a turbine with 17 megawatt, and I remain with the steam demand if it is say 45 TPH, and I am still at 45 TPH. So if my power demand is less, I cannot take 45 TPH. That we need to all understand. I think I am making it clear. So if your power demand, so suppose I have a 14 megawatt steam turbine and my steam demand is say 50 TPH or 60 TPH, just discussion per sake. So and I decided, okay, I have to put some more margin, so I will go for a 16 megawatt unit. But my steam requirement, I am not increasing. I am maintaining again at say 60 TPH only. So tomorrow, when my demand is actually becomes 14 megawatt, I will not get 60 TPH from the turbine, because my turbine, if it is coming at a lower load, I have to run the steam turbine. I have to provide lesser steam to the main steam, and therefore my quantity of steam coming out of the turbine will also be less. It is almost in a straight line relationship. Now, in a controlled extraction turbine, problem is extracted. What is controlled extraction? So, controlled extraction is a steam turbine where you give the main steam, and it is and here you have a condenser where you are condensing through a cooling water, or you can think of a air cooled condenser. So there can be a WCC or ACC based on if your water requirement, and we take extraction from steam turbine. Now we also need to know this extraction in a normal steam turbine, this extraction is called bleed. When it is called bleed, because in that case it is a uncontrolled extraction. That means here whatever is the steam flow, say there is a X steam flow which is happening here, and the power is P, and I design that this is coming as a Y steam flow is coming at P1 pressure, and suppose this is P pressure. Now this is power. So if the power, so the power plant is, say, just discussion sake, it is 30 megawatt power. Now tomorrow, if I am, because of the part load operation, this power is reduced to 24 TPH, then this P1 also is going to reduce almost in the same proportion. Basically, this P1 is a function of the flow rate. It is a direct proportional to the flow rate of the main stream. So if the main stream reduces, this pressure also reduces. However, for a extraction turbine, basically when you're talking about the extraction turbine, we talk it a controlled extraction turbine. So in a controlled extraction turbine, there is a control valve here, which is integral to the steam turbine. In that case, up to a certain level, mostly say up to say 30% or the 25% of the load, your whatever is your power demand, whether it is going down, no problem, your pressure is not going to change, it will be remain constant. So that is called controlled extraction steam turbine, which is used in a process industry. And in this case also, so that is how, but obviously this, with respect to this, the cost of the control extraction turbine is high, so the capital cost is high. However, at the same time, and obviously because I am condensing here, if you see I am condensing here, so I am putting some amount of heat to the atmosphere through cooling tower or ACC, so the overall efficiency will be low. At the same time, also just to highlight, though it is not a important for ethanol plant in that sense, but sometime it may be important. You can have a control extraction turbine from a back pressure turbine also. So if you have two pressure system, for example, you are using 6.5 kg pressure for distillation. Some technology allows that, particularly the European technology where the distillation is at 6.5 kg instead of 3.5 kg. And you can have a 3.5 kg pressure for you can have a 3.5 kg pressure for your process steam, for your drying system. So in that case, and this can be this we can have an we can configure for a larger, larger capacity plant. So here we can have a 6.5 kg pressure control extraction going to the distillation system, and here we can have a 3.5 kg pressure equivalent. There will be a pressure drop, of course, going to the drying section. So that can be configured in a back pressure turbine also. So these are the basically features. So back pressure turbines are cost effective, but this flexibility wise, this has a challenge. And control extraction turbine efficiency, if the turbine front, the efficiency is higher, but in overall efficiency of the system will be little bit lower, and the cost will be, of course, will be higher. So this is just a comparison out of it. So it is the thing, everything I have discussed. So for a back pressure, for example, it is a simple and direct process integration. Here it is a little bit complex process integration. And then the flexibility here, as I discussed, is low. Capital cost is also low. Operation complicacy is also low. So back pressure turbine is a very simple turbine, but only thing, the flexibility wise it has a problem. And to avoid that flexibility, for a higher generation of power and heat, one should go for a extraction condensing turbine. Now, coming to the next subject, that is the feed water heaters. I'll just take a 1 minute break, bio break. I'll just come in 1 minute. Excuse me. I'm sorry. So we can start again. So next subject is whether where to use feed water heaters and how we are going to use feed water heaters. So basically, in any steam turbine configuration, I'll just go to the next slide. So any configuration, whether this deaerator will be anyways there, because it is not only a feed water heater, it acts as a to remove the oxygen from the system. But whether to use the HP heaters, or in some cases, in this back pressure case, there is no HP heater, it is only there is no LP heater. HP heater or not, that is a judgment we have to take. So how we will take that judgment? So what, first of all, we should know what is the function of a heater. So when you are putting a heater, so it enhance the efficiency of the power cycle. How it enhance the power cycle? So for that we have to just little bit have a small discussion on the Rankine cycle. So this is a Rankine cycle, and this is the temperature entropy diagram. So you will find that here we are putting the feed water heater, and because we are putting the feed water heater, you will find that the boiler inlet temperature is increasing. So otherwise, here the boiler outlet temperature, so inlet temperature will be, say, in this case 151. In many cases, it is lower than that, say 130 degree, 120 degree. So here when I'm increasing the boiler inlet temperature, and if I go back to my original slide where we are discussing the heat rate. So if you see that boiler inlet, see, if you see this energy, when I'm giving it as say at 120 degree centigrade, so I am giving a lesser energy to the boiler, and when I'm giving a 200 degree centigrade or maybe 190 degree centigrade, then I am giving a higher energy back to the boiler, and therefore, and obviously for that there is some power loss. So if you do the math, you will find my overall fuel consumption is going to reduce. So that is why in many cases, particularly for a little bit higher side megawatt, where we are going for a 13 megawatt 15 megawatt unit, we should put at least one HP heater. And secondly, we can combine the extractions. Suppose for this particular case where we are discussing, say particular case, from there also I am taking an extraction at 7.5 bar, and also I am taking extraction from here, which is going to extraction to the process. Also from this extraction only, or this is the exhaust from the turbine, which is this is a back pressure turbine, I am taking to the deaerator, and here from this extraction only I am giving to the process. I have taken another extraction here to enhance further. So this may or may not be required. So that cycle analysis has to be done, where you have whether you can use a HP heater or not. Even if you do not have this, suppose we don't have this extraction requirement, still you should have at least one HP heater in the system when your megawatt is around 13 to 20 megawatt. And if you go beyond 25-30 megawatt, you should have at least two HP heaters. So therefore, feed water heating involves multiple stages. So there will be low pressure heaters, where obviously low pressure heater where we are using condenser. The deaerator is a direct contact type heater, which will be anyways there, because we have to scavenge oxygen from the system. Also, it acts as a preheater. Basically, it acts as a heater where heat changes the temperature of condensate or the DM water to a level, to a certain level. So for example, if there is only a deaerator for a smaller unit, say 5 megawatt or 6 megawatt unit, in that case you are giving the entire mecha to the deaerator at 35 degrees centigrade. DM water you are going to give, and the process makeup is also coming to the deaerator. So in that case, and the process makeup will be around 60 degrees, 75 degrees centigrade. So we are enhancing the temperature from 60 to 75 degrees centigrade, and if you mix it up, it will be around 50 degrees centigrade to a level of say 105 degree or 120 degrees centigrade, which acts two ways. So it is acting as a heater as well as oxygen scavenger. But you may have to increase the feed water temperature further to reduce the boiler fuel consumption. Also, it acts as a, for example, if you put a higher heat to the boiler, suppose this heat I am putting at 220 degrees centigrade, so the absorbed heat generation requirement by the boiler. So this is the enthalpy of the main steam. So this is 824, and this is the enthalpy of feed water, those 220. So this difference is, say for example, 604. Now this portion, if it is coming down to say 120, then not only my, obviously my fuel consumption will be higher, but also my boiler will be bigger. So the capital cost wise also there will be some saving if I introduce feed water heaters. Then there is an interesting subject particularly pertain to the ethanol industry is the dam condenser. Many of you have already using condenser, and many of you are going to use condenser. To me, basically, the dam condenser is a waste of energy. Not only it is a wasting the energy during the dumping process, but also it is wasting the energy continuously, because you cannot stop a cooling water line of a dam condenser based on your requirement. Suppose you because you simply do not know when your steam demand will fall, and you will dump the additional amount of steam to the dam condenser. So you have to continuously run the dam condenser, and I don't know your experience, but in my opinion, you have to continuously run the dam condenser, and you have to maintain the vacuum, and you have to run the cooling water for that. So cooling water consumption or the cooling water pumping cost is a continuous cost. So if you can calculate the cost, it is not coming, it is not going to come in a small cost. And anyway, when you are dumping, that is a waste of energy, all we know. However, for a islanding plants which are running in islanding mode, this dam condenser is must, because you cannot predict exactly how much power is going to be power demand, and how much will be the steam demand. But for a plant which is connected to grid, I think it is, in my opinion, we can avoid dam condenser to a larger extent, because you have a sink called grid, where from where you can draw power, where you can export power. Obviously, you have to contract accordingly with the power distribution agency. So, because using a dam condenser, point number one, it is a capital cost, though it is not a big capital cost, but it is a continuous loss of power. And when you are dumping, you are lost. There is a continuous loss of energy. And in some plant it is possible, because of the particular plant configuration. We are not at all able to balance between the power and steam. In that case, we don't have any option but to go for dam condenser. Now coming to the last part of our discussion, that is boiler. Obviously, you all are there has to be a boiler when you're talking about a cogeneration heat and power plant. So basically, there is a three types of boiler we have seen in the particularly pertaining to your industry. I am not touching about anything for waste heat portion. We are talking about basically fired boilers. So one is travagate boilers, which we call TG boilers, ABC boilers, CFBC boilers. So if you see this, all these boiler technology, so I'll come back to the slides again. So if you see, there is a, in the travagate boiler, so there is a grate which is moving and coming back, and the fuel is on that. Fuel is fed on that, and it is fired here, and then combustion gas is coming out. So it's a very simple boiler. However, this has its own limitation, which will come to the next slide. And the fuel burnt is in the fluidized bed, and the second part is the ABC boiler, which we call a APC boiler, where it is a bubbling, where there is a bed, and on that the fuel is bubbling, and the fuel is burnt in a totality in that sense. And that is why, but here it is at atmospheric pressure. It is not at a reduced pressure, it is at atmospheric pressure. So that is why it is called a ABC boiler. And there is a circulating fluidized boiler. There are two, three technologies. One technology, we come with a one technology called IRCABC boiler, and our and other companies come with other technology where they use cyclones. So there are some difference there. I'm not going to that difference. What is the difference between Thermax boiler versus other people's boiler? Simply fundamental is that the fuel is fed and the fuel is burned in suspension. That means this entire bed is actually gone up and it is burnt in a suspension, and the balance portion the balance solid goes to the system through a cyclone, or in Thermax case there are U beams where it from where it comes back to the furnace. So, and it is similar technology is similar to FBC boiler because it is developed from FBC boiler technology, but the burning is at a higher velocity and the burning is in totality within the furnace. It is restricted within some height of the furnace. It is in totality within the furnace, and therefore there will be higher efficiency. We will find that AFBC and CFBC boiler, there will be efficiency difference around 1.5 to 2.5%, depending on what kind of fuel we are going to burn. So the question is, what technology as a buyer you are going to select? So if your fuel flexibility is, if you see TG boiler, the fuel flexibility is moderate. So if you are decided that I am going to run the plant predominantly on a biomass plant, and fuel is more or less you have decided like bagas or something like that, so you decide for a TG fire boiler. And obviously the steam pressure range, I will come to the steam pressure range after this, and the capacity also there is a restriction. You cannot go a TG fired boiler of a 200 TPH capacity or 150 TPH capacity, because other than in that case it will be a very big boiler. So there are certain restrictions, but it will be a cost effective for a lower TPH and lower capacity plant, and particularly when you are going for a biomass plant. You can burn obviously coal here, but for economic purpose you should go predominantly on a biomass, say 70% biomass, 30% coal, 80% biomass, 20% coal, or 100% biomass. The AFBC, you will find there is a very high fuel flexibility. So you can design it for multiple fuel. You can design it for Indian fuel. You can design it for a very high ash fuel, which is predominantly in the eastern part of our country. Even you can have the fuel which is having washery reject as high as 45 to 50% of ash. Efficiency is medium. It is in between ABC, TG boiler and CFBC boiler. Emission control, obviously it has some feature of emission control, but it is not as high as CFBC boiler, so you cannot have a very stringent emission control in that. Obviously the particle size is not a problem. With SOx and NOx, it will be difficult to meet in the today's norm. Steam pressure is in medium. I'll come to the next slide where we are going to discuss the steam pressure. And it is basically best used for the coal-based plant, and where you are going for a mixed fuel plant, where you can have a say 50-50 mix between the coal and the biomass, or 60% 40%, and where you are looking for flexibility of fuel. You are not sure. Obviously nobody is sure from where exactly the fuel will come tomorrow. Nobody is so sure. In that case, the AFBC boiler is very suitable. Similarly, CFBC boiler and obviously there is a capital cost difference between the TG boiler and AFBC boiler. AFBC boiler is slightly costlier than TG boiler. Now the next technology which comes is CFBC boiler, which is fuel flexibility wise is very high. Thermax has supplied some boiler where they have burned some 10-12 types of coal, and this is true for all the CFBC boiler also, not only for Thermax. The efficiency is very high. Emission control, we can have emission control as for SOx and NOx, where the efficiency is very high, which is proven in the market. And we can go very high pressure boiler, and basically it is predominantly by coal. We can have mixed fuel. We can have mixed fuel as high as 35-40%, and we can have more than that also. But in that case, because we are burning the fuel in suspension, and it is little bit lesser than the atmospheric pressure. So in that case, your boiler will become very high. So your capital cost versus operation cost will not be suitable if I go for a very high percentage of biomass in the CFBC boiler. but still some people are going for that, but that is for a different consideration. Now, so how to select a boiler? So just a guideline here. Before that, I'll just touch upon the steam portion of it. So this is a enthalpy versus entropy diagram. The steam pressure selection, though it is related to boiler, is basically related to your steam turbine. So what happens if you go for a higher pressure? So this is enthalpy and this is entropy. So if you go for a higher pressure, your enthalpy is more. So suppose this is the inlet of the steam turbine, and this is the outlet of a steam turbine. So amount of work done by the steam turbine is this point to this point. Now if I can push this point higher, so my amount of work will be obviously higher. So as we go for a higher pressure and higher temperature range of a steam turbine, your power cycle will be more efficient. But you cannot increase to the infinity. So obviously there are certain considerations. So obviously the technology selection is based on, as I told you, the capacity of the boiler, fuel used in the boiler, requirement of emission control, and Opex and Capex of the boiler. And then what is the rule of thumb for selection of a boiler? So every time you cannot do a calculation. So the rule of thumb is if you are between 40 to 45 TPH, basically you can go for TG fired or AFBC. Basically TG fired will be selected for a biomass kind of thing, AFBC for a biomass and coal mix up kind of thing. For a higher capacity 50 to 75 80 TPH, straight away you should go for ABC, should not look for TG fired, but still you can look TG fired if you want to go for a lower capex, but your Opex will be higher because the efficiency will be low. And above 75, obviously you should go for a CFPC boiler. Here also ABC is a choice, but beyond 100 110 TPH, ABC should not be a choice. For a biomass fired boiler, again the similar thumb rule you can put. AFBC can be well established. AFBC technology is well established in the biomass technology. And only you have to see when you are using the biomass, we have to see what is the chlorine content in the biomass, and that is important because if you go for a higher pressure with the chlorine content, there can be chlorine fouling in the superheater. So you have to restrict the pressure between 45 to 66 bar when there is a moderate to high chlorine in the system. So chlorine. So when chlorine is not a constraint, you should, for a 5 to 12 megawatt unit, the ideal pressure, the optimum pressure temperature is 67,490, and it is more than 12 megawatt, say up to 20-25 megawatt, 110 out of 515, or maybe up to 30 megawatt also, 110 out of 515 degrees centigrade is the recommended pressure temperature. So we're coming to the last part of our discussion where we are just summarizing this thing. So steam and power demand profile is very important, and we have discussed how to evaluate that. What is the ratio heat to power, process steam pressure and temperature requirements. So all these things obviously has to be defined. Fuel availability and type has to be defined, and the grid connectivity and power export possibility also has to be evaluated. And thirdly, we have discussed about the technology selection. And obviously, as you all know, with all these things, we have to come to the Opex and Capex calculation and accordingly select the plant. So that's my presentation. Any question you have, we can discuss, or you can put in a chat box, we can discuss. I think you can put your, I think there are already some chat box.
The session is now open for questions. Please feel free to share your question.
Or you can put it on a chat box, not a problem.
Yeah.
I can put it on there also.
You can put it on a chat box also. So, sir, we already have 3 questions in the chat box.
Yeah.
So the first question is how we can minimize the losses by sudden power cut or steam cut by process?
Yeah, see, if there is a steam cut from the process, obviously if you go for a back pressure turbine, back pressure turbine, then the power is also going to be reduced. So in that case, it is essential you have an alternative power source which is synced with the system, particularly with the grid. Ideally, when the process is reduced and the power is from the from a back pressure turbine is also reduced, obviously it will be reduced. Then the grid power will come in. So grid power will compensate that. However, as we discussed from some cases which is not related to ethanol, where there are projects where the control extraction turbine is supplied, this will not be a problem. The turbine will take care by itself.
Good afternoon, sir.
Good afternoon.
Sir, suppose we are doing the running the plant through the turbine, we are getting around 30 ton steam. Suppose we
Yeah.
are getting bypass steam 5 ton from the PRDS.
Yeah.
The heat loss, how much will be there?
See, the heat loss, say 5 ton steam you are taking from say 66 bar and reduce
Yeah.
it to, for your case, maybe 5-6 bar. Okay. So you can calculate yourself that what is the enthalpy. See, basically when you are putting a pressure reducing station, basically you are reducing the pressure. So the enthalpy difference is the in terms of kilowatt per hour is the loss, and if you divide it by 860, you will find out the loss in terms of kilowatt. So you can find that loss because in that case it is 5 mega. Ideally, you should not do that unless you have a compulsion to do so. Ideally, you should run this 5 TPH also to turbine because it is going to do some work from 66 bar to 5 bar, even if it is 6 TPH. So that will yield some amount of power actually.
When through the PRDS, we are getting the more steam, right? When reducing the pressure, we are spraying the water, PRDS session. So
Then you are using some energy, but that is a part load condition where your power demand comes down, but still you have a demand for steam, correct?
yeah, so still some heat losses will be there.
There
Even
will
though
be a
PRDS
considerable amount
condition.
of heat loss. Say so for a 66 bar, your enthalpy is around say 790 or so, and you will reduce it to an enthalpy of 650. So that differential into the mass. So that amount of heat you are going to lose in the pressure drop.
Okay, sir. Thank you.
Okay, thank you. So what we can do because of the time,
Good evening, sir.
how can we maintain the boiler efficiency as low load means if our boiler runs at 70% load, how can we control the parameters? See, at 70% load, your boiler efficiency is not going to come down drastically. There will be hardly 0.25 to 0.5% difference is coming on the boiler efficiency. There will be some drop because the efficiency is calculated at the highest point because it is a boiler. The efficiency is calculated based on loss. You will not have a very high boiler efficiency loss, very minimum loss. But beyond 60%, you will not be able to control the temperature. That is most important. As your boiler capacity comes down up to 50% to 60%, you will be able to maintain the controllability in the main steam temperature. Beyond that or below that, you will not be able to maintain. So there is a question, interesting question, where it is a perfectly balanced. Nowhere it is perfectly balanced because it may be balanced in the paper, but actual case it is not a balance because finally the mode you are going to run the plant may not be exactly matching the way the originally it is envisaged. So there will be some constraint here and there. Obviously, it is not perfectly matched. And
Good evening, sir. Good evening, sir.
good evening, Mr. Gulshan.
Sir, we have one question. What should be the minimum temperature at the inlet of ESP to minimize dry flue gas loss as well as tunnels of ESP?
See, the ESP is the interesting question. ESP inlet temperature depends actually based on how much you have sulfur in the fuel. So if you have a sulfur in the fuel, then there is a sulfur dew point, and the ESP cannot handle any sulfur dew point. So if you have some sulfur, so generally the ideal temperature with coal, where you have a minimum sulfur, is around 140 to 150 degrees, 140 55 degrees centigrade. But and also in the biomass, also it is maintained around say around 135 to 1 degree centigrade. But if you are using a very high sulfur coal and you are not abating the sulfur, in many cases you are not abating the sulfur for some reason or another, then you have a problem. Then you have to see what is the sulfur dew point. So between the sulfur dew point and the actual temperature of that boiler outlet should be around 20 to 25 degrees centigrade gap. Secondly, that heat loss will be there. You cannot have it because if there is a sulfur loss, it will corrode the entire system. So you have to have that kind of temperature at the back end.
Okay, thank you, sir.
So there is one more question from Sumit Chauhan. How we can control the SOx, NOx in the fuel gas out from boiler?
Yeah, so that is also, see, SOx control see, generally in a AFBC boiler or a CFBC boiler. SOx control is through dosing limestone into the furnace, so that the lime is converted into calcium carbonate and the sulfur calcium sulfate. Calcium carbonate converts to calcium sulfate, and therefore you are reducing the sulfur. NOx cannot be controlled directly. It is depends on the boiler designer how much bed temperature he maintains. So the thermal NOx can only be controlled through that. Even if it is not controlled, then you have to go for a denox system where you have to dose ammonia into the system to reduce the NOx. So where we found some TG fire for 100 TPH. See, 100 TPH TG fuel is a very, very high capacity boiler. Okay, very, very big boiler for a turbojet boiler. So turbojet boiler, it is quite possible. But the volume of the boiler or the steel goes into the boiler is very high and the efficiency is low. So why one should go for a TG fired boiler? It is better to go for a bubbling fluid technology AFBC boiler in that case. And these days, the cost of TG and AFBC does not have that much of difference. That's just for your information.
So, sir, there is another question from Anuj Kumar Sharma. We are going for 300 KLPD ethanol. Our boiler selection is AFBC 60 TPH, 67 kg CM2 and turbine 8.9 megawatt. Can we go with dump condenser? Please suggest condenser.
Here in this case, you have to first study the HMBD from whoever you are taking the offer, and just ask them in that based on this your 60 TPH, and what is the process team, Mr. Anuj? So whatever is the process team, we have to see whether you have some excess steam available or not. Now, in that case, if the excess steam is available, then you have to start fast activities to start to finding out how to use the excess steam in form of extracting some steam for heater and all. So if every effort fails to avoid dump condenser, then only you should go for dump condenser. One of the way to reduce the requirement of dump condenser is to taking some extraction and put it to the heater. Another thing is a specified dosing ammonia. 3.5 kg, I know, Anuj, but what is the quantity if you can sell? I think whoever is your EPC partner, they can help you, because the suggestion I am giving that you can put some heater in the system and start to and think that how to and avoid the additional steam coming out of the extraction.
So there is one more question from Sridhar Babuji, Radico Organics. So we are having excess power. Can we use this power to increase feed water heating by heater?
Yeah, you can do so. So when you are using a feed water, your power also comes down. Though the efficiency goes up, your power comes down. So if there, but your turbine should have a provision. Right now, you might have purchased the turbine. If your turbine have a provision, you can definitely do that. And for all new turbine, we will like to encourage to use more of heating system to enhance your efficiency. But however, you have to be a little bit cautious for a lower megawatt, 5, 6, 7 megawatt. it may not be feasible because your cost may not, there is a cost associated with that. So that feasibility also has to be seen. Run on higher moisture due to rain season. How achieve efficiency? See, if you have a higher moisture, you have to sacrifice efficiency. There is no way because the boiler has to heat that moisture. So you can, so that there is no way you can reduce, you can maintain the efficiency. You have to try to reduce the moisture content by putting it into a shade or something physically, but boiler cannot help you in that case. How much minimum load? So minimum load is around say 20%, 15 to 20%. Maximum 25%, maximum 15, minimum 15% to 25%, depending on the manufacturer. So that much of minimum load you can run. How to control CO2? CO percentage in the bagasse fat. This question I am not very sure what is the question. So ma'am, what we can do, I am just putting my mail ID in the chat box. So any further question you can mail it to me, I'll definitely answer. I think it is 5:10 already. That's fine.
Okay, sir. So just give me a second. Okay, so
I'm putting my mail ID in the official
yes, sir.
ID.
Sure, sir. Please, sir.
So any other question you let me know, I'll definitely answer it.
So with the last question, we let us conclude the webinar. So we are very thankful to Mr. Ratnadeep Sinha sir as a valuable knowledge partner. Please accept a token of appreciation from GEMA.
Thank you.
Thank you, sir. Thank you all for your valuable time and participation. Good evening, everyone.
Thank you.
Thank you,
So
sir.
I am signing off. Thank you everybody for joining.
Thank you,
And
sir.
any
Thank you, sir.
feedback or any feedback or any suggestion or any other thing question you have, kindly mail it to me.
Okay, sir. Sure, sir.
Okay.
Thank you so much.
Thank you, everyone. Thank you.
Thank you.
Thank you, ma'am.
Thank you, everyone.
Thank you, sir. Thank you.